Right, so in today's video we're going to be introducing the sine rule, which is a rule that we can use to find unknown side lengths and angles in non-right-angled triangles. This rule will also work in right-angled triangles, but SOHCAHTOA is much quicker in right-angled triangles. So please don't overcomplicate the already simple problems. If the triangle's right-angled, SOHCAHTOA, find the unknown length or angle, okay? If the triangle's non-right angled, then we're going to need to make use of our sine rule or the cosine rule, which we'll introduce in the next video. So you'll notice I've jumped the chapter a little out of order by doing the area of a triangle before the sine rule and the cosine rule, but the reason I did that is it's actually because the sine rule comes from us being able to formulate the sine rule comes from understanding the rule for the area. Okay, so in our previous section, we know that the area of the triangle pictured opposites, this is our most general triangle, corners labelled capital A, B and C, opposite side lengths labelled lowercase a, lowercase b and lowercase c. And we know that we find the area of this triangle by doing half times BC times sine of A. Okay, so that's making use of these two lengths and the angle in between. Or we could do half times AC times sine of B, making use of those two lengths and that angle. Or we could do half times AB times sine of C, making use of those two lengths and that angle. Okay, so and that would depend on what information we've got. But we know that all three of those calculations will equal the area of this triangle. And so therefore, all three of those things must be equal to each other. That means that half times BC times sine of A must be the same as half times AC times sine of B, which must be the same as half times AB times sine of C. Okay, so we've got half in every side of the equation there, so if we multiply all sides of the equation by 2, we can get rid of those halves. And then if we divide every side of this equation by ABC, so let me do that so you can see where that next line comes from. So if we divide by ABC, on the left-hand side here, the B and the C in the numerator will cancel with the B and the C in the denominator, and so we just get left with sine A divided by A. In the middle, the A and the C in the numerator will cancel with the A and the C in the denominator, and we get sine B divided by B. And in the right-hand side, A and B on the numerator will cancel with A and B on the denominator, and we get left with sine of C over C. And so we get this. And this is the sine rule. It's worth noting that if I know that 2/3 equals 4/6, which it does, it's also true that 3 over 2 equals 6 over 4. If we have one fraction equal to another fraction, we can flip both sides of the equation. So be careful about that. It's not that, if you've got 1/2 plus 1/3 is 5/6, it's not true that 2 plus 3 equals 6/5. Okay, you can't just flip each part of an equation. But if we just have one fraction equals another fraction, okay, then we can flip both sides. 3 over 1 is the same as 6 over 2. Okay, so here we've got a fraction equals a fraction. We've actually got three different relationships here. Sine A over A equals sine B over B, or sine A over A equals sine C over C, or sine B over B equals sine C over C, but we can write them all in the one thing because they're all equal to each other. And we've got a single fraction on each side of that equation there, so we can flip each one and get the same relationship still. So these are both the sine rule. Okay. Now again, we can flip around the letters and we can call them P, Q and R, and it doesn't really matter what's A, B and C. What I really want you to focus on is this sense that sine of angle A, when I divide it by side length A, is the same as sine of angle B when I divide it by side length B. Okay, and that's also the same as sine of angle C when I divide it by side length C. So sine of an angle divided by its opposite side length is equal to sine of another angle divided by its opposite side length, which is equal to sine of the third angle divided by its opposite side length. Now when we're solving problems here, we're not going to need all three parts of the sine rule. You might just be looking at angles A and B, so you might just look at that little equation. You might just know about angles B and C, so you might just look at that little equation. It doesn't really matter what A, B and C is, so essentially your equation is going to look something like this, or you might choose to say side length A divided by sine of its opposite angle is equal to another side length divided by sine of its opposite angle. It doesn't matter. What I would say to you is solving equations is always easier if you put the unknown at the top left of your fraction. Okay, so if your unknown is an angle, I would be going with the top version of this rule and have the angles and the unknowns on the top. If your unknown is a length, I'd be going with the version of the relationship which has the lengths on the top. Okay, again, let's have a look at executing this. So find the value of x correct to two decimal places. So the key thing with the sine rule is that we need to be able to use opposite angles and side lengths. Okay, so in order to use the sine rule, you're going to need to know at least one pairing in your triangle where you know the angle and its opposite side length. Otherwise, the sine rule will be useless to you. Okay, and then we want to find x, so we actually want to think about using this angle over here. Okay, so we don't know that angle, but we have got enough information to find that angle. Okay, so I'm just going to label that theta. Let's just work that out quickly. So theta is going to be 180 minus 58 and minus 79. So let's just do that over here, 180 minus 58 and minus 79. So that missing angle is 43 degrees. Okay, so let me label this. That's going to be 43 in there. Okay, so it's about thinking about those opposite pairs. So again, let's start with the unknown thing at the top left of our fraction. So our unknown thing is a length. So I'm going to have lengths on the numerators of my fraction. Sorry, so x divided by sine of the angle opposite x. So sine of 43 is going to be equal to, now we're going to use the 12 because that's the other side length we've got, 12 over sine of its opposite angle, which is 58 degrees. And then we want to solve for x. Now again, we can do that rearranging by ourselves. So we know that x is going to be 12 over sine of 58 degrees multiplied by sine of 43 degrees. Just note that you can write that as the same fraction because sine of 43 is over 1. So you could write that as 12 times sine of 43 degrees all over sine of 58 degrees. That's the same thing. Okay. And so then you could type that in your calculator. Control divide, 12 times sine of 43 on the numerator divided by sine of 58 on the denominator. Again, you wouldn't need to write that as the one fraction if you don't want. You can leave it as 12 over sine of 58 and then outside of the fraction do multiplied by sine of 43. It's the same thing. Okay. But again, I want to be clear about the fact that if you have to use your CAS after you've done some simplifying, why not just solve it at the beginning? Okay, so you could solve your equation, which is x divided by sine 43 equals 12 divided by sine of 58. And we're solving for x. Oh, control enter. Okay, so you're going to need to use your CAS at some point in this calculation. So you can either do the rearranging by hand and then use your CAS, or you can just set up the equation and immediately use your CAS to solve that equation. Okay. There's no bonus marks gained by doing the by hand work at that intermediate step. Okay. All the same, you might find that sometimes it's a bit more fiddly entering in the solve and the comma x. You might find that where the rearranging is easy, and in this example, just multiplying by sine 43 is pretty easy to do by hand. You might actually find that that's an easy step. It's quicker to do it that myself and then just enter in the expression, so I don't need to actually use my CAS to solve. I just use my CAS to evaluate the expression. So you might decide that. So this is where, again, it's about familiarity. It's again about being used to using your CAS, knowing what's quicker for you and what's whether it's going to be more efficient to use your CAS early on or a bit later on in the calculation. Okay, so x is 9.65. X is a length and it's in centimetres, so 9.65 centimetres. I also want you to add in an element of does my answer make sense? Okay, let's be really clear about the fact that in a triangle, the side length opposite the biggest angle is the biggest side length. So this side length over here, I'll call it y, that has to be the biggest length. That's the biggest angle in the triangle, 79. So it must open out to the biggest side length. Our unknown side length that we're trying to find is actually opposite the smallest angle in this triangle. And so therefore, our side length has to be the smallest length. That means it has to be less than 12 centimetres. So if you got an answer here that was bigger than 12 centimetres, a bit of logic must be used for you to say, that can't be right, I've done something wrong here. Okay. Similarly, you also want to think a bit about the scale of the triangle here. Like, if all of your angles were 60 degrees, this would be an equilateral triangle. So all the side lengths would be 12. Okay, so they're not all 60-degree angles, but they're not a long way away from 60 degrees. So you shouldn't have side lengths that are significantly different from 12. Okay, so for example, if you found x was equal to 1.65, I'd be thinking, it doesn't really make sense given the information that I've got in the triangle. And I want to be clear about, it's not about me looking at the triangle and saying that side length looks like it has to be more than 1.65 centimetres. It's about the information in that triangle tells me that that length has to be more than 1.65. So we never assume that the triangle is drawn to scale. Okay, it's about using the information. All right, let's have a look at B. In triangle ABC, angle A is 52 degrees, side length A is 10 centimetres, side length B is 7 centimetres, find angle B. Okay, again, it might help you to draw yourself a little triangle. What are we going to have here? 52, I don't know, let's make that 52 degrees. That means side length A is opposite that, so that makes that 10 centimetres over there. Side length B is 7 centimetres, that's smaller than 10, let's put that there. And so therefore we want to find angle B. Right, so this time it's an angle that we don't know, okay? So we're going to do sine of angle B. So remembering unknown thing on the top left, start with that. Okay, so sine of the unknown angle over the side length opposite that angle, so that's 7, has to equal sine of 52 over the side length opposite that. You can't mix around, so you can't have sine B over 7 equals 10 over sine 52. If you're going to choose to have angles on the top, on both sides of the equation, you have to have sine of the angle on the top. Okay. All right, so then we've got an equation. Now again, we could do some rearranging here by hand, okay? And I'll write it small here just so I've got room. If I did that, the first thing I'd be doing is multiplying by 7. And then I'd need to do inverse sine. Okay, and I can put whatever that is in my CAS. Now, I want to be clear about this, and I actually actively don't suggest that you do this, because we'll have a look at a particular situation in a minute. You could potentially miss out on a correct solution by doing this method. I would suggest that you always use your CAS directly to solve to find what B is. Now, one of the problems that we're going to have here is if we solve our equation for B, let me just put this in my CAS and I'll talk about what's happening in the CAS information underneath, because that's important. If we solve this for B, so menu 3.1, control divide to get my fraction, sine of B, I'm just going to use lowercase b in the CAS, it doesn't matter. You could use x, there's only one unknown in your equation, equals, control divide, sine of 52, sine of 52 over 10, and then outside of the fraction, comma b, so we want to solve this equation for b. Now if I enter this, put this in and press enter, I'm going to get a horrible ugly thing happening here, okay? Even if I press control enter, horrible ugly thing happening here. And that's because this equation has infinitely many solutions, and this comes back to our understanding of what was happening in the unit circle, okay? If you're asking yourself, let me just go over here for a minute, if you're asking yourself, sine of what angle equals half, for example, thinking about the unit circle and sine being the y value, okay, there's a y coordinate of half here, and there's a y coordinate of half here. So actually, there's more than one angle which will have a sine value of a half. Actually, there's infinitely many angles that will have a sine value of a half, because you can keep going around and around the circle. So that's why my CAS can't give me a specific answer to that question, because where the thing inside the sine function is the unknown thing, there's infinitely many possibilities for that. So we need to give our CAS some more information here, because there aren't infinitely many answers here. This is a triangle, and we know that the angles all have to add up to 180 degrees. Okay, so let's think about what we know for B. So we know we've already got 52 degrees in the triangle, which means that 180 minus 52 is 128. So we know that there's only 128 degrees left in this triangle. So we know that B is going to have to be somewhere, well, it can't even be equal to 128 because then there wouldn't be anything left. It has to be bigger than 0 and it has to be less than 128. So we need to tell our CAS, okay, we want you to solve this equation, but we want you to solve it where B has to be somewhere in this particular range of values. Okay, so we do that. I'm going to scroll up twice here to get to my equation. I'm going to press enter to copy it back down. And I now want to add in this restriction. It's really important. The place people go wrong, students go wrong in these questions, is they put the restriction in the wrong place. So the restriction happens outside of the solve function. So you've done your solve equation, comma B, close the bracket to end the solve function. Then outside of that bracket, we're going to put this restriction. And we use the given that symbol. So press Control equals with your CAS. So we're looking for this vertical line here. So we want to solve this equation for B, given that B is between 0 and 128. So we're going to type 0 less than, so Control equals for your inequalities. 0 is less than B, which is less than 128. Now, if you use the letter x in your equation, you're going to need to put x in that inequality. You're solving for x where x is between 0 and 128. If you use some other letter in your CAS, then you need to put some other letter in, the same letter in your inequality. So now we want it to solve this equation, but we want it to solve this equation not to find the infinitely many solutions to the equation, but to find the solution that is between 0 and 128. Control Enter, sorry, for the decimal. And so we find that if we do that, B is 33.48 degrees. Now you could just always make your restriction 0 to 180 degrees, but it's better if you make a more precise, accurate restriction given the information in your triangle, because that will ensure that you get all of the solutions, because we'll see in a minute that sometimes there might be 2 solutions. Okay, so there's a bit of information about your CAS here, using CAS to solve equations to find trig ratios. So this example here, the first example, it's a length that's unknown. If the length is the unknown thing, you don't need any restriction at all. Okay, the length is unknown. It's only when it's the unknown inside the sine function. Okay, sine of x. Then you're going to need to add in the restriction. So in this second example here, where sine of x, we're going to need a restriction in order to be able to solve that particular equation. Okay, this talks about, again, making sure that given that goes after the solve function, that you use Control equals to find the given that symbol, and press Control Enter to get a decimal, use Control equals to find your inequality. So all that information is in that box there. We've just talked that through with this specific example. Okay, let's have a look at this example. Number 2. Triangle ABC, B is 39 degrees, side length B is 28 centimeters, A is 41 centimeters, find A. Okay, so let's see what we've got here. Let's have a 28 and 39 and 41, and that's the angle that we're trying to find opposite the 41. Okay, so again, let's set things up. Let's start with our unknown thing. Sine of our unknown angle divided by its opposite side length equals sine of 39 degrees over its opposite side length. Okay, let's think about what we know about A here. So we've already got 39 degrees in the triangle there, which leaves a further 180 minus 39, so 141 degrees for A and the other angle. So A has to be somewhere between 0 and 141 degrees. Okay, so when we solve this equation with our CAS, we know that we're going to do menu 3-1. You don't need to write on the paper that you're using your CAS. If it's a test or an assessment in which, oh sorry, I should have pressed my Control divide to get my fraction. If it's a test or an assessment in which you have your CAS, then I immediately know, if you write down an equation and then write down the answer, that you've used your CAS to solve it. You don't need to tell me that. Okay, divided by 41 equals sine of 39. Sorry, Control divide. Sine of 39 divided by 28. Solving for A. Now, because A is inside the solve function, we're going to need that restriction. So given that, Control equals, and this vertical line, 0 is less than A, which is less than, what did we decide? 139. Control Enter to get your answers as decimals. Okay, so my CAS tells me that A is 67 point, what do we want? One decimal place, 67.1 degrees or 112.9 degrees. Okay, so let's have a think about that. So neither of these angles actually make the triangle add up to more than 180 degrees. So why are we getting two different answers? Are there actually two different answers? So actually what's happening here, let me draw a slightly different and a bit better triangle. Okay, so let's say we've got that. So let's say this is 41 here, this is our 39-degree angle here. Now, I originally drew the triangle to say, okay, well, let's make that sort of 28. So I drew it as if this angle up here, angle A, which is what we were trying to find, is an obtuse angle, or an angle, oh, well, actually it's a bit, let's say, let me make that a bit more extreme. Let me just so that you can see that a bit more clearly. Try not to. Okay, so let's say 28, that one was. So I drew that as an angle bigger than 90 degrees. So that would match with the diagram I've just drawn, that would match with this being 112.9 degrees. Okay, but what we need to think about is it would be possible to imagine this red side length I've drawn as a pendulum. And imagine that it's fixed at this point here, because we can't change this blue length, this length here. So it's fixed, and we can't change the angle of 39 degrees. So it's fixed up there. But we imagine that red length is like a pendulum, and we can swing it around so it now comes in here. And again, my diagram's not very well drawn to scale, and now this is my 67.1 degree. Now obviously that's not 67.1 degrees, so my scale's a bit out, but you get that sense that actually, no, sorry, I've drawn this the wrong way. My apologies. Because 41 is fixed as well, so we can't change to 41. So it's not going to swing that way, it's going to swing the other way. So we imagine if this length could be extended out, because that blue length is not fixed, okay? And instead we imagine being able to swing this red length around this way, sorry, because I was changing that 41 at the bottom. And now instead this is still 28, because we haven't changed the length of it, we've just swung it around like a pendulum, but now this is 67.1 degrees, that's an acute angle there. Okay, so there's two possible triangles that we could draw. The green triangle around the outside, and again, I haven't got the best scale here, or the red triangle here, and both of those triangles fit the criteria where you've got a 39-degree angle, the side length opposite that is 28 centimetres long, and you've got a 41 centimetre length, and the angle opposite that could either be 112.9 degrees or 67.1 degrees, depending on how you choose to draw the triangle. Okay, so this is what we call the ambiguous case, and this is where it's important that we have some understanding about the unit circle, about the fact that there are two possible angles that give the same sine value. Now sometimes not both of those angles will be, one of those angles will be more than 180 degrees, and hence it doesn't make sense in a triangle. But sometimes, like what we're seeing here, it's possible that both of those solutions could make the triangle work. And so we actually have two correct answers, and you need to be able to give both of them. This is where, if you do this solving step by yourself here, you won't get both solutions. If you use inverse sine, it will only give you the solution between 0 and 90 degrees. And then you'll have to do another step to check whether or not there's another correct answer. Hence, the best way is to use solve and to restrict the value of A to make sure that if it gives you two answers, those are two correct answers. If it only gives you one answer, then there's only one answer. Okay, so I strongly recommend using solve. So as I said, we call this the ambiguous case, where it's possible that the sine rule could give two possible answers, and that's because the information provided could describe two different triangles. Okay, the information is ambiguous in that it doesn't just precisely describe a particular triangle. So again, there's another example here. You've got 35 degrees, 10 centimetres and 6 centimetres. So this time we're imagining we can take the 10 centimetre length is fixed, so we can't change that, but we can take this 6 centimetre length, treat it like a pendulum, swing it around this way, and get another triangle which also has a 6 centimetre length, a 35-degree angle, and a 10 centimetre length. And so therefore, if we're trying to find the angle in here, angle A, there are two possible values for angle A. And we can see that happening over here in the CAS. We've found either 107 degrees or 73 degrees. So this would be the 107 degree option, this would be the 73 degree option. So two different triangles with the same information. Alright, so that talks that through there. Alright, so exercise 4F, so I really want to encourage you to use your CAS to solve, particularly when it's the angle that you're trying to find, because that will ensure that if there is more than one correct answer, you will find both answers all at once. Alright, so 4F are the questions you want to work on today.